Hello, students. This brief tutorial will add to our current unit on gases. I would like to use this packet that was placed together and authored by Mrs. Emily Miller. She is just well known for these I do, we do, you do packets. So here are the objectives that will be covered in this brief lesson: a revisiting and applying of the kinetic molecular theory of gases. So, of course, we've already talked about these postulates that describe a perfect and ideal gas. Well, we're going to try to apply and interpret this a little deeper. Look at how would we draw and illustrate differences in temperature, possibly amount with particulate models of gases, and then looking at the Maxwell-Boltzmann distribution. All right. Can we look at this first particulate diagram? Now, this particular one is showing we would anticipate individual atoms of an element. So maybe helium, maybe argon, and they're actually also indicating relative speed. We know it's a gas because of the particle separation, but also because of the movement. We know they're moving in rapid, random, chaotic motion. Now, the length of the arrow we would use for comparable speeds. So this arrow is shorter than this. So this would be traveling at a smaller speed than this, or a lower value than this. Well, why? I'm sure that this is conveying to us a certain temperature, maybe room temperature, maybe 50 degrees Celsius, not sure. And we know temperature is a measure of the average kinetic energy. Average. Given a certain temperature, there are going to be particles that have greater kinetic energy, lower kinetic energy, and then a whole lot that have in between. And that's what's being shown here. A gas traveling at a lower speed, an expression of kinetic energy, a higher value speed, expression of kinetic energy. We know that gas particles, when they collide with the walls of the container, exert pressure. And so that's what the arrows are showing us as well. All right. Next, we talked about the relationships of most of the variables that you can measure about a gas. Remember, we said if you have a sample of gas, you can measure its pressure directly or indirectly, its volume, its temperature, and its amount in moles, which we would be measuring likely grams and then converting to moles. And this is just the reminder, not necessarily that we need to know the specific chemists that are credited with gathering the information that we attribute to these mathematical relationships. We just need to know the relationship of the variables to each other, and that if we're only looking at two of the many variables that can change the others. So if we're just trying to see the relationship of pressure and volume, if we increase volume, what happens to pressure, and vice versa? Well, then temperature and amount need to be constant. So we just need to remember that as well. And if we would graph these variables, how would they look? All right. Maxwell-Boltzmann distribution. Remember, we just said that given a sample of gas, not all the gases are traveling at the same speed. So a Maxwell-Boltzmann distribution is the relative amount. So here it's number of molecules versus speed. We are being shown three collections of gas. I'm not a big fan of the terms cold and hot here. So we understand that this would be a lower temperature. So why don't we just go ahead and say 0 degrees Celsius. Room temp, 25 degrees Celsius. And then hot, why don't we just say, why don't we go with 65 degrees Celsius? All right. We need to be so careful because most students interpret height of peak to match temperature. No, height of peak is just the number of molecules that are traveling at that speed, the number at that speed, the number at that speed, and so on and so on. Okay, so this is not because it's the highest peak, the highest temperature, and this is not the lowest temperature because it's the lowest of the three. Now, can we just examine, let's say, this red curved area? So if we want to go ahead and call the top of the peak, that's okay, our average. And we have some that are greater and some that are lesser. Here's our average that then we would compare to this, to this. Now, if temperature is a measure of the average kinetic energy, as we increase temperature, we know we're increasing kinetic energy, the energy of motion, which will be shown as an increase in speed. So if we just look at, well, here is what we're just choosing to be the average. So that's the temperature of the red, the average. Here, the temperature of the green, and then here, the temperature of the blue. So don't be distracted by the height of the peaks. Look at where that peak is hitting for comparison. So we're told here, but we could also infer that the blue must be at a lower temperature. The red is at the higher temperature. Okay. Now, why the greater distribution, the higher the temperature? The greater the value. So if we just go ahead and, just for comparison's sake, since I chose the lowest temperature to be 0, why don't we set the bar at, or the beginning, if you will, at negative, let's say 5, all the way up. And I want to choose, maybe we'll just go to 90. Okay. So we're saying that the average of 0, okay, and there's going to be a distribution, some lower in temperature, some higher. Then at 25, it's up there, yeah? And we have some that are lesser and some that are greater. And then we have the 65, and we have some that are lesser and some that are greater. The greater the value, the greater the distribution of possible greater and lower. So the smaller the value, the more restrictive the range will be. The greater the value, the broader the range will be. We could also, infer that if we are trying to find the area under this, I betcha these are trying to represent all the same overall number of molecules. So maybe we have 5 moles, and 5 moles in our 3 different samples. So that's why the same amount of particles, because we're at a higher temperature, we're going to have more showing a greater range than, for example, the blue. And we'll talk about this more. But the higher the temperature, you can have some that are barely moving. You can some that are kind of, that are, kind of, that are really moving, and that are really, really moving. Where a lower temperature, you have some that are just kind of moving, just kind of moving, and then are moving, right? So the greater the number, the greater the possibilities. That's why we have a greater distribution. All right. So let's go right to this. And if you want to go ahead and read what you're being asked to do, pause, see what you can come up with, and then compare your drawings to mine, and I'll go through an explanation. All right. We're given this as our reference. Remember, number of molecules versus speed. Okay, now we're asked to show if the gas would be heated. If the gas would be heated. So we have the same amount. The only thing we're changing is the average kinetic energy. So we know if we say the quote unquote average is here, that at a higher temperature, you have a greater kinetic energy. But I need to just spread out the total number a little more broadly. So, it doesn't say that we need a dotted line or anything like that. So this would be the new. Now, we're not told how much the temperature has changed. So as long as the new curve is definitely lower, but yet broader, and this like peak, which you could call the average, is indicating a higher speed than the first did. Okay, we are going to learn the relationship of molar mass on speed. So the speed of a gas, we will learn, is actually represented by root mean square velocity. So you know that, usually we use a cursive V for velocity, but we'll talk about it's an average of a great variety of sample values. Okay, well, the speed increases when the temperature increases, but your speed decreases when the molar mass increases. The heavier the gas at the same kinetic energy will be traveling slower. So a gas with a higher molar mass at the same temperature will be traveling slower. All right, so here is our average. Okay, so we have to show that, the greater the number are here. And remember, the smaller the value of our x-axis, the narrower the distribution. So if we're trying to represent the same quantity, then this one we would draw because it's going to be a higher peak then. All right. So as long as we're showing that, we're going to have to heighten it, there's going to be more particles because it's less of a range, and our average is lower than the average here. We got it. All right. Some gas was removed from the vessel. Temperature held constant. Some gas was removed. So our number of particles is going to change, but temperature, same average. Now, I hope we understand why we had to show a lower speed. And the reason the lower speed is because of the greater molar mass, not a change in temperature. Okay, but here, same temperature. So we would respect the average, but at a lower temperature, or I'm sorry, at less molecules, they're going to be about this. So as long as it's below and then your peak matches the peak there. Oh, I don't like that hotter. So a higher temperature gas was added to the original gas, allowed to reach equilibrium. All right. So we know when two samples of matter are put into contact and they're at different temperatures, heat will flow from the higher temperature to the lower temperature. So if we say that this is at 100 degrees Celsius and this is at 75 degrees Celsius, well, depending upon what the gases are, if they're the same gas and the same amount, well, then we're going to end up at a temperature in between. However, we have no knowledge of that. But we definitely know that we're going to increase the temperature of the original, increase the temperature. And they're asking how this will change. So how do we show a higher temperature? Well, that's going to be shown as a greater speed Yeah. And then we have to distribute a little more broadly. Okay, there we go. All right. So what if we were asked to draw particulate diagrams? What this is asking us to do is apply our understanding of the relationship of volume, temperature, amount, pressure. Okay, this is our reference. And our reference is a 1 liter vessel. Same volume, same volume, same volume, same volume. Great. 1 mole of H2. Hence, each of these are hydrogens. They're overlapping, and so we know they're bonded. And the temperature is 200 Kelvin. So if you want to pause now, come up with your own drawings, and then we'll compare. So here, the only change is double the amount. So if 3 molecules represented 1 mole, we need 6. So 3, 4, 5, and I'll put a 6th one here. Ooh, need to have them touching, of course. And because, let's see, that these look about the same length, and that's a little shorter. So I'm going to go ahead and make that shorter, but this longer, and then this about the same length, and then shorter, about longer, and we'll do longer. All right. A 1 liter vessel containing 1 mole of neon. Same temperature. Okay. Neon compared to hydrogen. Hydrogen is 2.012, if you will, gram per mole. And then neon is 20. Okay, neon is 10 times the mass. So it, at the same kinetic energy, will be traveling more slowly. Neon also is bigger, and it is monoatomic. So I'm going to choose to draw that in red, still a mole. So 1, 2, 3, that a little bit bigger. And then go ahead with 3 of the hydrogens. It's the same temperature for the hydrogen. So I will draw them approximately the same as here. So a long, and a short. And then, let's see, I need, roughly just a fraction of this. So maybe this is moving in this direction. This is moving in that direction. And then that direction. So we should be showing these as larger. That's, denoting different atom single spheres because it's not a compound, and shorter arrows. All right. Only change lower temperature. So not as much kinetic energy. Our arrows will be shorter. So we had 2 long and 1 short. So I think I'll draw the short as my long. Ooh, really short, really short. All right. 2 moles of hydrogen. So I need 6. And then, we've doubled the temperature. So these are going to be longer. Yeah. So I'm still going to show like one kind of short, but longer than this short. Oh, did I do that? Now we know we're going to have, a bigger range. So maybe I'll do one that's kind of in between the short and the long, and then definitely another longer one, and I think another long one. All right. So we've gotten experience with particulate diagrams showing the relationship of our different variables. We've looked at Maxwell-Boltzmann distribution, and have accomplished what this packet was aimed at.